Gernot Akemann that will talk about random point processes in the plane and application to birds of prey. Please.
Thank you, Andrea. So first of all, I would like to thank the organizers for giving me the opportunity to present work here. It's a great pleasure and a great honor to participate in a workshop for Philippe's birthday. I've been here as a postdoc from 2001 up to 2004, so this gives a lower bound how long we know each other. We have one joint paper, well, actually a book we edited together on random matrix theory, but hopefully there will be many more years to come, so we will see. Okay, so I will speak about something that will hopefully please you, Philippe, as I know you like birds. So this will be about random point processes, and as you will see, it will have something to do with nests of birds of prey viewed as a random point process. But there will also be some, I think, very deep and open mathematical question related to that, where Philippe has contributed, and we have discussed this, namely 2D Coulomb gas at arbitrary inverse temperature beta, as you will see. So the work I'm presenting is joint work with a group of behavioral biologists led by Oliver Krüger in Bielefeld, with two different subsets of people, in particular Michael Barker from mathematics, who brought us together to work on this subject. So this is the outline of my talk. I will start showing you some examples for point processes as they occur in ecology, and in particular regarding to birds, what we will look at. The second part will be about a mathematical description. Of course, you may imagine you start with random points in the planes that are independent and don't interact. This will be Poisson point process. Then I will talk about random matrices, obviously, just a great place here in Saclay to talk about. But neither of them will be the right thing, so we will have to think about some interpolation, and I will show which path we took. And then I will show you how this path works in application to birds of prey in the Teutoburger Wald. And after some discussion, I will have also a picture for you, Philippe, at the end. Okay, so this is the first example for spatial patterns of trees. This is taken from this paper here. So these are three different kinds of trees. It's not so important. So this is beech, Norway spruce, silver fir. You see that, well, they have several very interesting features. First of all, the density is not very homogeneous here. So there are places where there's a very high density and of low density. You see also that these people here have included some further information, namely the dots here have different size. So this different size is what they call density at breast height. So for me, this would be here. So that's where they measure the diameter of the tree. And so this point process also includes information about how big the trees are. This is not something I will consider later, but this is something in this example here. And so obviously people would like to understand, based on this point process, what is the influence of environment, let's say nutrition, terrain, of the population density. And as you can imagine, there are not only beeches here on this picture, there are also other plants. So maybe you want to see how do they interact, and can you see that on such a very simple approach, just looking at the point process of these trees. Here comes a second example. So this is the area of Bielefeld. This is where my home university is and where I live. Perhaps you can see very faintly there's a green strip going through here. This is the Teutoburger Wald, a forest which is very beautiful, but also rather infamous because the Roman legions, led under Varus, had one of the most decisive defeats in the Roman Empire in this area, probably a bit further north. But that's not what we will think about today. So you see these dots here. So what are these dots? These dots are nests that are occupied in the year of 2020. This is an area, to give you an impression, of about 12 kilometers times 25 kilometers. So it's an area of 300 square kilometers. And what these biologists do, they go there in March and April and check if a nest is occupied by the common buzzard, which is the species we are looking here at. And if on both occasions the nest is occupied, it is qualified as nesting. And so these are the blue dots here. So there are also blue dots outside this area, but they can only do this area every year, okay? So we will focus on the area where there are blue dots and look at this point process. Now you also see perhaps there are holes, like there are cities. Bielefeld is a big city, Werther is a small city. We will ignore that because of reasons of statistics. So we will take this, if you like, in random matrix language as the bulk of the spectrum. So there's no edge here because there will be birds continuing living here, but they are not monitored. And what is also very important, I talked to them and they say they're not missing a single nest. They are very confident about this, okay? So they're not missing points. Good, so this is something we would like to try to describe with a simple statistical mechanics approach. Now, after our first paper on buzzards, we became more courageous, and so we included also two other species called goshawks and eagle owls. I'll show a picture very soon. And so what you see here are now 3 different colors. So the size does not, okay, the eagle owls are indeed bigger, as you will see, but the nests are marked by the points. So these points are eagle owls, the yellow points are goshawks, and the blue points are as before. And we have also marked now a strip which approximately marks the forest. Now there are several things you can observe here. So for example, the yellow dots have a very sparse pattern compared to the blue dots, and they're also quite regular. The eagle owls are very dense in the forest and very sparse in the plains, and we will have to deal with that. So here again the question is, can we quantify their interaction in some sense based on this point process of annual nests? So I should also emphasize every year is an ensemble. So we will look at one ensemble and then if we look at consecutive years, there will be independent ensembles. Otherwise, you know, if you mix different years, you will get Poisson, that is clear. Then you don't see anything. So here are the 3 protagonists. This is the common buzzard, a goshawk, and an eagle owl, and this is the order of size. So this is about 1 kilo, like maybe 80, 90 centimeters of wing spread here, a bit above, maybe up to 1.5 kilo, a bit more than a meter, and this is the eagle owl, who can weigh up to 4 kilos and almost 2 meter wing spread. These two I've seen, one of these in our garden, eating a pigeon, and this I've seen when going jogging close to dawn, because these two are active during the day, and these are active during the night. So that poses some further problem in the interaction. And so yes, can we quantify their interaction or repulsion based on the annual distribution of nests? So both within one species, compare the interaction strengths between different species, and then also perhaps say something about the repulsion between different species. Okay. Of course, this is very simple-minded, but let's see how far we get. So this is the first thing you would come up with. You take points that are independent, you throw them randomly, let's say on a disk or on an interval. So this is just to show you what is the effect of dimension. So the blue curve is what you would get for a Poisson point process on an interval. So the probability to have 2 points close to each other is very high. Whereas when you go to the plane, well, there's an area measure, so RDR, and so you get a linear repulsion, even though these points are random and not interacting, just from the area measure. So there's a linear repulsion here, but otherwise this is the effect of dimension for Poisson. The second choice you could make, of course speaking in Saclay, which has always been a big hub, many people working on random matrix theory, is to look at complex eigenvalues of non-Hermitian random matrices. And so here 3 ensembles have been proposed by Jean Genibre before I was born. So the distribution is just, so Jij are independent, real complex normal random variables. And these are scatter plots of realization. So you see they distribute on a disk. This is called the circular law in the large n limit. The density looks by eye approximately constant, and it is in the large n limit. However, there's a marked difference along the real line here. So for the real matrices, we have real eigenvalues. That's very easy to understand. The characteristic equation is real, so the solutions will be either real or complex conjugate pairs. So there will also be complex conjugate pairs. And for the symplectic one, there's a repulsion from the real line. Now, all these three ensembles have been completely understood as what we call determinantal or Pfaffian point process. So this is determinantal. These two are Pfaffian. I will talk a bit about determinantal if you don't know what that is. But it took more than 40 years in particular to understand and compute all correlation functions in this ensemble. Now, there's a very remarkable property, namely if you disregard the real line, the local correlations in what I call the bulk here are the same in all three ensembles. This was shown in, well, rather recently after the real Geneva ensemble was solved. And furthermore, there's a closed formula for the spacing distribution in the bulk, which is most easily computed in the Geneva ensemble, but as I say, in the large n limit, it's the same. So all three ensembles give the same point process in the complex plane. This formula here is based on what is called gap probability. We have seen that in Philippe's talk a little bit. Here, the thing is that you can compute the eigenvalues of the Fredholm determinant, which is diagonal, explicitly, and then from the probability of one eigenvalue at the center and the next one at radius s, you get the gap probability, and then you take the derivative, so you get the spacing. So if you don't believe it, physicists always like to do numerical simulations, so this is a check that indeed all three Geneva ensembles give the same distribution, and the black curve is the formula I just showed you, and it's an infinite product, but you can truncate it, it converges very quickly. So again, to show you the effect of dimension, this is what you would observe if you would take the classical Gaussian ensembles of Hermitian random matrices. So we also like acronyms in random matrix theory, so GOE stands for Gaussian orthogonal ensemble, U unitary, S symplectic. So here, the three ensembles are very different. And in particular, the repulsion here comes from a Vandermonde determinant in the joint density. So this goes with power beta, whereas before we had 1 power from the area measure and 2 powers from the Vandermonde, as we will see. So if we were to look at random points on the real line, we would have three ensembles which we know perfectly analytically to compare with. Here we just have one. So what do we do if neither of them works? Well, we will look for a mathematical description of a point process that interpolates between Poisson and, let's say, random matrix. So there are two proposals that I'm aware of. So one is in a very nice paper by statisticians, Möller et al. I think from Aarhus. So they assume that you can describe the point process you want to model as a determinantal point process. So that means all k-point functions, so density 2-point functions, are given by a k times k kernel. And the kernel is the object you will have to fit. And you will fit it, well, the 2-point function is a 2x2 determinant. If you take the connected part, you take the square root, you can fit from the connected 2-point function the kernel. This is not an easy task because it's a function of two variables you will have to fit. Now let's check that you can go to a Poisson limit. Well, if the kernel becomes diagonal, so it only has an entry when I and j are the same, then the determinant becomes diagonal, the point process becomes factorized, and that's obviously the Poisson limit here. Now that's not the approach we have taken. We have taken another assumption, which is also a strong assumption, but simpler in some sense. We assume that we can describe the point process by a two-dimensional Coulomb gas at inverse temperature beta. And then there's just one real parameter we have to fit, which is beta. Okay? This will not be a biological constant. It's just a parameter, but that allows us to make quantitative statements. And obviously, when beta goes to 0, as we will see, this leads to Poisson. And I should mention that we have applied this approach already in physics. There's a famous quantum chaos conjecture by Buhigas, Giannoni, Schmidt, and Barry Tarbos stating that for Hermitian chaotic quantum Hamiltonians, the statistics of the eigenvalues should behave like random matrix statistics. And if the system is integrable, it should behave like Poisson. Now this has been generalized to open quantum systems by I think Fritz Haake and the group, and so there the conjecture is for non-Hermitian quantum chaotic systems, the statistics will be Ginibre, or perhaps some other ensemble, and if it is integrable, it is Poisson. And we have seen this transition here in work with Thomas Prosen, who's a real expert here on integrable open spin chains. So how does it look like? Well, this is the Coulomb gas. So this is the Hamiltonian. So we have a logarithmic pair interaction. We have beta in front, and we have a confining Gaussian potential. So normally in statistical mechanics, you would pull out the beta of everything, but we don't want to do that here because we want to be able to set beta to 0 and still having a Gaussian confining potential. So when beta goes to 0, this Vandermonde to the power beta here will disappear. So we have Poisson, a Gaussian independent random variables, and otherwise we have strong correlations. Now this brings me to a very interesting and open mathematical problem, namely of this distribution, we do not even know the partition function. So this is what is also would be called a Selberg integral in the complex plane. So it's an integral over n complex variables. They have a Gaussian distribution, and we have a Vandermonde here to the power beta. Now you would say, okay, easy. We take beta integers and then do an analytic continuation. These are just polynomials. We have a Gaussian integral. Fine. No, it's not that easy. So there's a very nice work that Jean Bernard mentioned already on the Laughlin wave function from 94. And there are two results for arbitrary beta integer for n equals 2 and n equals 3. Now, my student tried a little bit, my fault to put also on this very difficult problem, and we discussed that with Philippe. We got very excited because we could see some pattern, but then in the end, it didn't work. When you go to high enough beta, the pattern was gone. So we could not make progress even to n equals 4. Okay. Now, you might think, okay, this is maybe some academic problem. It's an integral. Well, who cares about, apart from maybe people here in the audience? No. If you have the partition function for finite n, there's a very interesting phenomena. There's a condensation of the eigenvalues rather than sitting on a disk with a uniform distribution. They will condensate on a triangular so-called Abrikosov lattice. And numerical, this is conjectured since a long time. There's also very nice recent work here to happen at around beta 142. I don't know if this was in one of your birthday sequences, probably not. But and some of my mathematics colleagues don't believe that. So we should prove it. And if you have the partition function, well, you should be able to see the trace transition if it is there. Okay, so
is it a problem of having beta and even integers so that you can really get rid of the absolute values?
No. Well, you can try with even integers, but you have to see a pattern how it works for arbitrary, let's say fixed n, and then see how does it work for general beta. I mean, look at these formulas. I mean, they are, well, nice, but not a piece of cake. And I've talked to some people like John Keating, Peter Forrester has worked on this, I think, for more than 15 years thinking about it, but okay, I'll leave this to you. So what do we know about these Coulomb gases for arbitrary beta about local statistics? There's some work on global statistics using loop equations, but I'm really interested in local correlations. Okay, so for beta equals 0, there's a nice paper by Gauthier Lambert who showed that if you scale beta with n, so it goes to 0, but at a defined rate, it will remain locally Poisson. Okay. Then there's beta equals 2, where this is a determinantal point process. I should have said that, so that the Ginibre ensemble falls in the class of determinantal point processes because you have two Vandermondes. So you can easily show that this is equivalent to have a kernel, so a single determinant. So everything is given by a single kernel, which is a truncated exponential, basically. So what can we do? Well, we can do numerical simulations, as I will show you. And we also came up with a surmise, so like Wigner did for the pictures I showed for real eigenvalues, you can try with a 2x2 matrix model that has actually exactly Vandermonde to the power beta. So this was work of Patricia during her master's thesis. This is the formula. It works for beta equal 0. It's Poisson. It works for beta equals 2. However, the approximation is very bad for beta equals 2. So here the approximation is good, close to Poisson. in contrast to Wigner-Searle mice. Wigner-Searle mice gets better when beta is large. It's quite bad close to Poisson. So we did some, renormalization of beta. So as a simple formula, it works, but we will also do comparison with numerics. So here comes the nearest neighbor spacing distribution, determined numerically. So this is Poisson. I think Genève is about this curve here. And when I say nearest neighbor, it should be clear. So I pick a complex eigenvalue, and then I choose the nearest neighbor. That will be this one here. And then the distance S is this distance. So just Euclidean radial distance. And I will also need the next to nearest. Maybe this is maybe this one here. So this will have another distance. Because we will also compare with next to nearest neighbors to have some information about the range. Both for Poisson and Genève we have analytic results, but here of course we will do numerics. So let's go back. So this is snapshot 2020. Here I put for your eye just to see where we are heading. This is the upper half of the complex Genève ensemble. So you see they are repelling each other. And this is a lower half of Poisson. So you see they are much more clustered. So we want to fit this point process to either this and that. And this doesn't work. So blue is the curve from Genève. The repulsion is too strong. Red is Poisson. There is some repulsion, so it's not Poisson. So what we will do is we will fit these data. So these are histograms of the spacing distribution of the blue points I showed from 2020. And of course, we fit to the cumulative distribution to get rid of dependence of histograms of the choice. And we have a library of beta in steps of 0.1, so we can fit that. The other thing you see is that statistics, it's not very good. I mean, this study the biologists do is one of the biggest one worldwide on this kind of birds. Still, in this area, there are at present around 250 pairs breeding. And that's not very much if you want to have such a distribution. You need maybe 500, maybe 1,000 spacings to start to see something good. So we will have to do something, and what did we do? Well, we looked at time moving averages. So we took, we took some time, let's say an average over 5 years, over 10 years, and you see that, so the black curves are now the fits with Poisson. We get beta 0.7, it goes a bit down. And this is for the next to nearest, so you see the repulsion is much weaker. So it's not Coulomb, maybe no surprise. But we can quantify what is the repulsion for the nearest neighbor and for the next to nearest. So we can also find a time resolution here. So the blue is, it's a linear fit to guide the eye, but the real points are the blue points here. The red points are next to nearest neighbors, and we compared that with the development of the population. So the population has increased at the same time quite dramatically from 80 pairs to over 200, let's say 230. And it seems that this rise in population has also been paralleled with a rise in repulsion. And I should say that, if you have a density that is larger, the spacing will become smaller. So that's a trivial effect we have to remove, of course. So we will always normalize the mean density to 1 and then compute the spacing distribution. Okay, so because it worked, I would say quite well for the buzzards, we now also include the other species. So this is the buzzards again. So 1 year, now on average over 10 years, over all years, and this is for goshawks and for eagle owls. And you see the statistics becomes quite bad, but if it works for buzzards, why should it not work for the other birds? So we just tried. Okay, and you see that there's some hierarchy. So the highest repulsion is amongst goshawks. This is about 0.8. So there are about 400 pairs we could average over 20 years. And Oliver said, yes, they are the most aggressive species of all of them. So it makes sense that the repulsion is the strongest. Now what about population development here? It looks quite different. So you see for the goshawks, the population, well, let's look here first. It saturates, it goes down. And so the blue ones are again the nearest neighbors, and the red one are next to nearest. So the repulsion is even stronger than Coulomb. And here for the eagle owls, well, apparently the nearest neighbors don't really care at all. Okay, so this is about repulsion between different species. So maybe this is too busy. So the upshot is the repulsion, we can observe it, but it's very small. So this would be like between eagle owls and buzzards and eagle owls and goshawks. And we always, of course, pick those that are less abundant, and then we find the nearest neighbor, because otherwise we would overcount. Okay. That there's almost no interaction here between goshawks and eagle owls is probably at the limit of our model, because you have seen the population decline. So Oliver says they are under pressure. But so we need more statistics. We have to see. Maybe our model is not good enough. So maybe last investigation, when we gave a talk, several talks on the first paper on buzzards, people said, yeah, but I mean, what is about the influence of the terrain? So here I marked again for you the area in black cities, green forest, white plain. Now these birds have to nest when there are some trees. So they have to nest in some green area. So what we did is we just threw points at this plain, about same amount of as birds. When they fell on a green area, we accepted them. On white, we rejected. This is the histogram. So this plane has actually an effective fractal dimension of 1.66. So even if we found repulsion close to 0, maybe the true Poisson process would be even further away. So this is just to tell one thing. Okay, let me wrap up. So the influence of terrain we have seen. I think this is a remarkable thing that this works at all. So we have a very simple idea from statistical mechanics. We can fit a point process that knows nothing about physics and Coulomb gas. Beta is not a biological parameter, but it allows us to quantify the repulsion between within one species, between different species. We can see a time dependence. We can see that if the nearest neighbors repel more, then the next scenario is it is weaker than Coulomb. For the goshawks, we found this is stronger, at least on the local scale. Now, open questions are, of course, well, can we find some model from biology that is at least approximate Coulomb? This is not as crazy as it seems, because for 1D, there is some work by Peter Scheber on parking cars and birds on a power line based on psychological perception of closing a gap. But here, this is more complicated. So we don't have an idea here, hence 3 question marks. And Oliver says, let's meet again in 10 years and have more data. So with this, I would like to finish. This is a picture with Philippe and Gernot. We had a very nice walk when visiting MSRI in 2021. This is an area, a preserved area of redwood named after John Muir, one of the first ecologists in the United States, heavily influenced by Alexander von Humboldt. It's a wonderful place. So happy birthday, Philippe.
Thank you very much. Are there questions, please? Please.
Well, I know that this is a completely different story, but some Hamiltonian that I would put, some cost energy that I would put on the points to check, is the one for Monch-Kantorowicz optimal transportation from the nest to the terrain. Because, I mean, these birds have to prey in a region and do not overlap. So that one is problem I've been interested in, and there's nice things. There is a whole theory of Monch-Kantorowicz optimal transformation.
I will happy to look into this, but I mean we have been very simple-minded, and we just thought when they enter each other's territory, they start fighting, and one of them may die. So that's why they will probably not like to nest very close to each other. But on the other hand, the eagle owls, they're active during the night. So they make videos and ring the birds and make experiments. He showed us videos where the eagle owls came and grabbed first the young ones from the nest, and he said during the whole night he just ate 4 buzzards. And they could not do anything. They don't hear, they don't see them at night. So the interaction is complicated. So those active during the day, they shout, they hear each other. Maybe this is something to investigate also, how far this carries, but yeah. Thank you.
Please.
Should I do that? No, I do that.
people, excuse me, people keep talking about the decay of the number of birds. In France, at least, that's a hot subject. So I was quite surprised to see that one of your populations was tripled
Yes.
within 20 years or so.
Yes.
So was there any change, environmental change in the use of fertilizer, of pesticides or something that could explain that?
No, it's not so simple. I think Oliver was also surprised about this steep range, especially with the eagle owls. I mean, I didn't show the plot with population per year, but they almost had died out. And now there are 20 pairs, and they are not only in the forest area. They like to live in these quarries, but also in the plain. So no, I don't know the reason, but they hunt on little rodents, so mice, maybe also a rabbit, or maybe another fellow bird. So it's not like, you know, pesticides will infect these bigger animals, but yeah, I don't know if there has been a change in that sense.
I have a remark.
Yes.
For beta equal to 2, this is you call Ginebra.
Yes.
You can solve. I mean, it's cumbersome, but you can
No,
solve.
it's you know, it's everything you want to know, you can say.
Okay,
Analytic.
because you map to, for example, fermions in the lowest
Yeah,
Landau
yeah,
level,
yeah,
and then you can
yeah.
compute everything.
Yeah, we can compute everything
Yeah.
from beta to everything, gap probability,
Yeah.
smallest
Okay.
eigenvalue, largest eigenvalue,
Okay.
variances, you name
Okay.
it. Yes.
Okay,
Yes.
sure. Okay. Okay, please.
Yes, you could also try to draw the Voronoi cells of your points just to see if basically they all have the same area somehow, and
Yes.
what are the fluctuations of that? Have you thought about it?
No, but this is a good idea. Maybe just to look, I mean, so you see, the yellow points, they are very evenly spaced. I mean, so for the blue points, okay, we will have to see. But and I did not say, but I mean, we distinguished the birds, the eagle owls here and here, because these point processes are very different, apparently. But no, thank you. I mean, I will have a look.
Okay. More question? Okay, we thank